Hello, everyone. Hope you're doing well. If you have watching this one first, go ahead and make sure you're going back and looking at these videos in order, starting with our proof and sets video, which would have been the one from before this one. This video is going to be building off of the material that we talked about in the last one. So make sure you're kind of watching these in order. This one, talking about sets and functions, we'll discuss a little bit something of a different topic. We're building off of sets again, and of course, we're keeping all that proofwriting stuff intact. As we move to talk about a special type of set that we're going to see a lot of in this class, especially near the latter half of this unit or of our class here. So maybe in the second unit, we should be calling it. We will be dealing with our primary objects being functions, dealing with functions from one set to another. These are assignments, as we're going to see, of a particular type. You may have seen, we know about functions to some extent. We've seen f of x equals x squared. We may have even been in classes where you're in functions that could be just general piecewise assignments or other kind of strange types of functions. We're going to see a lot of functions in this class and deal with a lot of them in very particular ways. We're going to see some more what I would call perhaps strange functions, functions that don't kind of fit the same sort of mold of what we've seen before. And we're going to want to know a lot about the basics of functions and make sure that we have these down pat, ready to go for our upcoming sections. So sets and functions, we're going to see how these two things interact a good bit in this section. And at the very end, we're going to talk a little bit about how we deal with functions and look at series as well. So series, basically the kind of generalization of sequences that we've had before this class. So last time we were talking about sets, inclusion and exclusion and things like this, and we'll be doing a similar thing whenever we talk about functions. We define a function from a set x to a set y, and we write it kind of like this, to be an assignment which maps an element x in the domain set x to an element y in this is we say is equal to f of x in the set y. Our general kind of picture of this is that you have maybe a set x and a set y. And what is happening is you're taking an element x that gets mapped through f, and what it spits out is y. F accepts an input from the domain and then gives an output, which gives you an element inside of the codomain. Here, the codomain is the set that our function is heading towards. Some of you may have heard this and heard it called the range, but I'll be calling the range something slightly different. I'm going to say that it's the set of all of the function elements that actually are y values for a set. Let me give you an example in terms of f of x equals x squared. F of x equals x squared, I might write this function like this, that this is a function that goes from R to R, that has a domain of the real numbers and a codomain of the real numbers. However, this function does not have a range of the real numbers, because if I'm plugging in any element x and r, that's going to only give me a non-negative number once I plugged it through this function. So while the codomain of this function is r, the range of this function is the set of all real numbers such that x is greater than or equal to 0. So this is a difference between codomain and range. Range is a subset of the codomain always. The meaning it's always going to be some sort of collection of elements that are inside the codomain. That's exactly what the codomain is there for. It's saying this is the world in which you could envision these y values being held. So why don't I make this set the codomain? I absolutely could. I could absolutely make this set the codomain here, but when I'm talking about functions that go from the reals to the reals, what I'm trying to say is you could have functions that only really map to the non-negative functions. You never have to have it be the case that the range of the function f is the entire real line. In fact, this could be the constant function, f of x equals 0. That would only have 0 as its range for that set. But we would still call that a function from the reals to the reals. Its codomain could be considered the real line there. And given that you have these sets lining up in the correct way, namely that the codomain of one function lines up with the domain of another function, then you can make a composition between those two functions. So let's say, for example, that f is a map going from x1 to y1, and g is a map going from x2 to y2. Well, if it's well-defined, that is, if you could actually map something from the range of f and get it to be inside of the domain of the function g, then you can compose these two functions. You can think of this as like you have the map going from x comes through f and gives you f of x, and then take that f of x as long as it is in the appropriate set, plug it in through g, and get something that is in g of f of x. And this is the composition of those two functions. Notice here, what sometimes we will call the y value of a function, the y value given from up here, is now becoming the x function, x element coming into g. So as long as the y1 is a subset of x2, and in fact, we could even be more restrictive here. We could even say if f of x1 is a subset of x2, that is, if the range of the function f is a subset of the domain of the function g, then you can define the composition of these two functions by making your y value from the f of x function your x value for your g function. So this is the point in y2 that the function g would map f of x to. Just as we can map a point through functions like this, we can also map sets through functions. And let's be specific about how that looks. We will define f of a, where here capital A is a set inside of the domain of the function f, to be the image of that set, the image of A. And the way that that's defined mathematically is that you take the elements, all of the elements f of A, little a, where little a is inside of the set big A. Here, little a is an element of the set big A. So, for example, if I'm taking something like f of x squared, or f of x equals x squared as my function, and I would like to take a look at saying, okay, well, what is f of 1, 2? Well, then I would look to see what are all of the points in the function f, right? That the map from wherever my real numbers is, inside of the point 1, 2. Where do those points go? What are the y values that those could take on? Notice that it does not have to be a nice set. For this one, this would be the closed interval from 1 to 4. But it does not necessarily have to be a nice set. It could be that there are various points that it's strewn throughout. It's very possible that maybe you have a kind of a little bit of like an asymptote with some sort of value given in the middle here. So you could potentially get that f of a set is equal to the real numbers. So that's very much possible here. So that is the image of a set underneath a function. It's taking all of the elements inside of here and saying, I know that whatever point that I plug in inside of this set is going to live inside of this set somehow. So like, for example, this is 2.25. This is inside of the set 1, 4. It is exactly those points that have a point in the domain that get mapped to that point somehow, some way. Especially when discussing continuous functions, which we will be doing at some point very soon. So we'll have definitions of continuity starting in week 2. Then we will discuss the set F inverse of B. This is the inverse image of a set. Notice here there's a difference in how the set is defined. Here, this set A was a subset of the domain X of the function, where this is a subset of the codomain of the function. The inverse image of a codomain subset B is going to be all of the elements in the domain such that the y value associated to that x value is in my set. So for example, I might take a look at f inverse of the set -1, 1, wherever I have function f of x being the same as here before. So I am asking what x values are there that when I consider where they get mapped to in the function, they're somewhere inside of the set -1 to 1. And what I would get from that is something like this. I would say that, well, all of the x values that could get mapped from -1 to 1 are inside of the set from -1 to 1. And you can check this. Any x value from -1 to 1, if you square it, well, it's going to be greater than -1 and less than 1. And in fact, any other value that you could take on that is about outside of this set, either greater than 1 or less than -1, if you try and square it, you're not inside the set from -1 to 1. Now, some of you may have noticed a few things about this set that I chose here. The -1 to 1 here is interesting. You might say, John, why didn't you just pick the set from 0 to 1? Because if I'm looking at subsets of the codomain, well, I might as well be looking at subsets of the range for this function. And remember, the range of this function f of x equals x squared. That's just going to be the non-negative numbers. So John, is this the same answer? When I plug in f inverse of 0 to 1, am I still going to get negative 1 to 1? And the answer is yes, because if I'm looking at all of the x values that have y values going from 0 to 1 in this function, then what I'm looking at is still that same range. Looking here at wherever I could be looking at from going from 0 to 1, then the only way I can get those x values to work is to be inside of this interval from negative 1 to 1. But notice that would have been the same if I had written this as being, instead of the y values going from 0 to 1, if I had written the y values as going from negative 1 to 1. So let's say, for example, I draw this function back up on here, and I take my window of y values to be going from negative 1 to 1. And then notice that the x values that live inside this little y window is still the same. Even though there are no x values that associate to these negative y values, because there can be none for this function, that still doesn't change the fact that you can take f inverse of sets like that. So something that's interesting here is that if you took f inverse of the set going from negative 1 to 0, not including 0, that is, if you take any subset of negative numbers for this particular function, f of x equals x squared, well, then this is something called the empty set, and that's how we're going to write it. We write it here with a little circle with a slash going through it. Some people will always also write it like this, the empty set, meaning it has nothing in it. There are no x values such that their y values live within the set from negative 1 to 0, not including the y value of 0. So because of that, we could say that this set exists, but it is the empty set. It's not that it does not exist, it's that it exists and there's nothing in it. That is the empty set. We'll say that a function f is surjective if, whenever you take a look at f inverse of a single element y, that this has at least one element in it for each element y inside of y. So for example, the function f of x equals x squared is not a surjective function. I could take a look at f inverse of the set negative 1, and I would get the empty set. Because of that, I know that this has no elements inside of that, and this cannot be a surjective function. One way to think of that is whenever I have a y value for my function that I would like to plug in, and that's any y value inside of my codomain, I need there to be at least one x value that maps to that y value. We also will say a function f is injective if f inverse of y has at most one element for each y and y. That means it doesn't actually have two elements that go to it. Notice that this function is not an injective function based on something that I've drawn here. Take a look at this. If I take f inverse of the set containing 1, then what's going to happen? F inverse of the set containing 1, remember, f is injective if f inverse of this set has at most one element in it for each y value. But notice here, I'm actually going to get two y values for this y value of 1. That's going to be the set of negative 1 and 1. That shows me that this is not an injective function. So an injective function means whenever I pick a y value, I cannot have it hit two x values. Some people call this the horizontal line test for injective functions, which is that if something passes the horizontal line test, that means that it never had a horizontal line go through it where it hit exactly 2 points. This one failed the horizontal line test because there exists a horizontal line somewhere on the function that hits more than 1 point in the function. It hit 2 in this case. So that is a function being surjective and injective. Notice that surjective means you have at least one element in f inverse of the set containing y, and f is injective means f inverse of the set containing y has at most one element. There is some overlap here. There's a very special overlap, which is whatever happens when a function is both surjective and injective. Right, and so what that means is you have a bijective function. We'll be defining that in just a little bit. For now, we only need the definitions of surjective and injective for the theorems that are to come, but you may know about a bijective function. So we'll talk about that in just a little bit. But first, let's go through a proposition using some of this terminology that we've been looking at, namely looking at things like f inverse and f when it comes to functions. Let's start by looking at inverse images of some functions f going from x to y. Let's also take a family of subsets in our codomain, and let's consider what happens if I try and have some interactions between sets and functions. That is the title of today, and a big topic of what we're doing here in this class is to make some of these connections. So f inverse, a property of a function or a mapping that is associated to a function. And then here, a union of collection of sets, which is back to an interaction between sets. We're seeing how these interactions work together. So F inverse of the union of this arbitrary collection of sets from a family cursive B here, this F inverse of a union, the inverse image of a union of sets, is the union of the inverse images. And similarly, if I had gone through and plugged in intersections, that's what this proposition is saying, is that inverse images of unions, same as the unions of inverse images, and the same thing is true for intersections. Now, maybe it's a little bit tricky to see how these sorts of what these things are kind of trying to say without some sort of picture to kind of help us go through this. So one way that I usually am trying to picture functions is I am taking x and y to be some sorts of sets inside of here. This is how I try and imagine what functions look like. You have x and y, two various sets, x being the domain, y being the codomain, and you're taking a collection of sets B inside of here. Some of them may be out here, some of them might be over here. And you're saying, what happens if I look for all of the functions or the sets F inverse for each of those sets so that when I map them through F, I get to those specific functions? Well, it turns out that the union, if I union these two sets together and take a look at their inverse images, then that's the same thing as unioning each and every one of the inverse images there. That what I get there is the same set. It might be worth trying to draw pictures of some of these propositions while you're using that. I will try and do my best to give some sort of starting directions and how you might draw some of these pictures. Like, what's one way I might be able to visualize functions? Maybe this is useful for you, or maybe you find some other sort of interesting way to get this sort of off the ground for you. But my recommendation is, when you're not able to visualize a proposition we talk about in this class, draw a picture of it. Once you've drawn a picture, it's going to make a little bit more sense about how we're supposed to go through and prove it. Like here, for example, I could start by taking a look at points that are inside of these sets that I'm looking at, these kind of parts of B, and then start looking at what happens when I take their inverse map, and then use some parts of the definition to help me out. Here, for example, it kind of looks like, well, there's maybe something just natural about the function that's making this work. So we're going to try and use the definition of inverse image to try and help us out. So here we're going to use this for the first equality. That's this one right here. So this is the first equality that it's mentioning. The second one, we can leave that up to you at some point. This might be at some point a homework exercise. And even if it's not a homework exercise, my recommendation is try and finish it yourself. Model it after what we are doing in the proofs that we're doing in class. So let's prove the first equality here. Let's start with an element that's in F inverse of the union of this arbitrary collection of sets. Then there's going to be some point x inside of x. So this is going to be using the definition of F inverse, such that f of x is inside of, and I don't need that parentheses here, the union of this arbitrary collection. So f of x is here in the union of these b's. Well, this point, f of x, is going to be in one of these sets. That's the definition of being in the union, and I'll call that b prime. Okay, so f of x is inside of b prime is exactly what we're saying here. Well, what does that mean? By the definition of inverse image, that means that x is inside of f inverse of b prime. But take a look at where we're trying to end up. We're trying to say that x is this element that we're starting with is going to be in this union of these f inverses of these primes. So x needs to be, because x is in f inverse of one particular set b prime, therefore x is in the union of these sets all taken together. So these are the sorts of steps that we're taking here. I also noticed that there's a typo here. I really should have said that this y value here was actually an x. So I should have said that this is x. So what could I have done instead to go through and correct that? I could say now there is some point x and x such that f of x is inside of this union. Well, what that means is that I do not need this part. So since x is inside of f inverse of the arbitrary union of these sets B, then it's f of x is inside of the union of these sets B by definition of inverse image. So there we go. We've kind of gone through and caught a typo while we were doing this. Let's keep going now with the other direction. Here, again, I'm going to catch it this time. Let's take a arbitrary element inside of this union. Let's call it X. Be inside of the union now of these inverse images of the sets. This is this arbitrary collection union now, but it's not the collection B, it's the collection F inverse of B. Notice here there's maybe a different order of operations in which we're considering the relationship of B, especially in conjunction with F inverse and this union. In the first part, we are saying you're taking the union of these B and then F inverse. Here, you're taking F inverse first and then the union. Then there is some set B inside of this arbitrary collection such that, well, X is inside of. Oh, I guess here I actually caught it. Oh, good job, me. I actually am just using a different letter here instead of using the letter X as to be separate from the first part. Whew, I thought that I had made the same mistake as I had made up in the first part, but I had not. So we are good to go. Then there is some set B inside of this arbitrary collection such that, well, Y is in F inverse of B. And let's call that set B prime so that Y is in F inverse of B prime for one of these sets that's inside of this union. Well, what does that mean? We're just going to use the inverse image definition again, but notice we're kind of going the opposite direction of how we were doing it in the subset argument. So F of Y is inside of B prime. Well, what does that mean? F of Y is in the union of these B, which means that Y is in F inverse of the union. Notice that we've just kind of gone through and undone the operations to get to what they actually mean and then tethered them back on. Hopefully some of this starts becoming a little bit more methodical to you after a while. It's like, how am I threading on and off these operations? It takes a little bit of practice to try it yourself, but it does become pretty good and becomes a little bit more like, oh, okay, yeah, this is that same sort of argument. We use a term in mathematics that's sometimes called follow your nose. And that means you're kind of just doing a little bit of what your intuition or your past experience has told you to do when approached with a specific problem. And that's exactly what we ended up doing here. We can just kind of follow our nose by using the definitions that are given to us here. I recommend this is an exercise trying to do now the same thing with the intersections rather than the unions, but I will tell you that the proof is very similar. Now, this is with inverse images, and you might think that images, the ones without F inverse, just with the function F, are a little bit easier to deal with. But the truth is that they're actually a little less wieldy. They're a little more unwieldy. So here, for example, I get a very similar statement in this proposition as I did up in the previous one, but you might notice a few small changes. Let's start here with a family of subsets, now a subset in X, so that's in our domain here. Then for all functions F going from our domain to our codomain Y, then the image of the union is the union of the image sets of each individual set in your arbitrary collection. However, you only get a subset relationship whenever you're looking at intersections. Now, this subset relationship can be strengthened, but it can only be strengthened whenever F is injective. That's what this proposition is saying. It's saying that you get equality in the same way that we did in the previous proposition whenever you have unions and you're doing this kind of switcheroony with the two operations. But with intersection, you don't get that. So let's see about this second statement when F is injective. So here now I'm going to be looking at the second statement. My recommendation after this is to try and do the first statement on your own. So this way, because F is injective, I'll be able to prove both parts of this equality. I'll be able to remove this and put an equal sign there instead. But notice that when I'm using the other direction for this subset, then I'm going to need to use the fact that F is injective. We'll see that here in just a little bit. Well, first, we can note that the intersection of all of these sets all together, so the inside of this function F, well, that's going to be inside of F of A prime. Let's take a look at that real quick. I think I left off an F here. There needs to be an F right here. There we go. Notice here that if I take a intersection of all of the sets A, and if I look and compare that to any of the individual sets A prime inside of my arbitrary collection of sets, well, this is a smaller set. So I can use that as a little bit of a guide. This is a smaller set than A prime for any A prime inside of our set, our arbitrary collection A. So what is going to happen then if I go through and map these images? Well, the F of this smaller set is also going to be smaller than f of a prime for any of the individual sets that I would plug in there. And the reason for that is if I plug in fewer x values, all contained within a set with more x values, well, then the possibilities for y values just expands. I'm not losing any y values by expanding the number of x values that I could plug in. And that's going to tell me that this subset relationship is true. Okay, well, so if something like that is true, then I'm going to be able to map it through just like this for all a prime and a. This seems like a repeat statement and tells me really what I was trying to say was probably just what I was trying to say from before, that the subset of x values is smaller when you take the intersection. Well, what does that mean? That means that if I take this to be true for all f of a prime, notice here, f of the intersection of a and a for all of these sets is a subset of f of a prime for each individual set. Now notice that's true for all a prime. So what that's going to mean is I'm going to be able to take an intersection now instead of just over an individual one. I could take a look at the intersection of maybe two of these sets. Maybe I have a prime and f of a double prime. Well, this intersection, f of this intersection of this arbitrary collection is inside of f a prime, and it's also inside of f of a double prime, where a double prime is another element inside of this arbitrary collection. That's the definition of being in the intersection. I can take that argument all the way to the extreme. I can, instead of just looking at an intersection between any two elements, I can take a look at the intersection between all f of a's and take a look at something like this. And because each of these individual f of a's contains this set, the intersection of all of these f of a's is going to contain this set. And that's exactly what's being said in this final line. So this final line right here is saying that I can write f of this intersection of a to be inside of the intersection of all f of a's. If it helps, write that out a little bit. Say a little bit about what's going on there, and that can help maybe make a couple of the pieces fit as you're going through this. So I'll go ahead and make that little bit of a correction there. I didn't need that f of a prime there. I just needed a prime to make my argument make a little bit more sense as I read through it now. So I've gone back and made that correction to that part of that statement. Now, that's the only direction we're able to prove when we are faced with an arbitrary function. If we are given that that function is injective, however, we can go ahead and make one more step. We can actually get this other direction going on. And let's take a look here. Keep a highlight on for this latter half of the proof for wherever something is using injectivity. So let's start with a y value, and let's say that that y value is in the intersection of the images. So we're starting here from this opposite set and trying to end up in the first one. Well, what does that mean? Y is inside of f of a for all sets in my arbitrary collection of sets here. Well, what does it mean? By y being an f of a, that means that there is an element x inside of the set A, such that f of x is equal to y. Now notice that that's something that is relative to the set A that I'm choosing. However, I'm able to just call that x rather than an x that's reliant on A exactly because of injectivity. Since f is injective, there can only be one such x for any of our sets A. That is, if I had chosen an a prime and an a double prime, for example, and I had the same element y that's inside of both of these, then the set x that gets mapped to y, well, then that has to be exactly the same. Remember our picture that if you have something that's not an injective function, then what's happening is you have a point, a y value, that could potentially have two x values associated to it. So remember, this one's not injective. So injective functions do the opposite. You could be looking at a function here that only has, for every y value, at most one x value associated to it. Well, so that means that if I'm looking at y inside of a prime and there's some sort of x inside of the set A that maps to that, well, then that element x is not going to be important whether or not I'm looking at a prime or a double prime, because by our sentence here, x is actually an element inside of, in this case, a prime, and x is in this case inside of the set a double prime. That's by our definition of image there. Well, if something like this happens, then think, those x values could be very different if this function's not injective, because they're in different sets. I'm not even assuming there's any overlap between those two sets, in which case, of course, they would be different. But because f is injective, I am forcing myself to have some sort of overlap between those two sets. And the reason is both of these have y inside of both f of a prime and f of a double prime. And x is the only possible element in the domain that could get mapped to this y in f of a prime or f of a double prime. So since f is injective, there is only one such x that is regardless of our choice of set A that we have here. So we must conclude then that x is inside of this set A. Okay, so that's because it's inside of each of those individual things. Well, since this is true for all A inside of this arbitrary collection, then x is inside of the intersection of all of these sets A, and hence y is in f of x, which is f of x, is inside of f of the intersection of A, which is exactly where I wanted to end up. So I'll do a little discussion of this down here, a few notes on this since it's a good bit different. First, notice how I'm using A prime sometimes rather than A when talking about a set. I do this especially in that first part. I'm using A prime, distinguishing it from the letter A. Think about how it would have been a good bit confusing if I had been using the letter A instead of A prime whenever I'm trying to talk about the set A, where A here is just an arbitrary element inside of my collection of sets. In which case, that would have been a little bit confusing. So oftentimes when I'm trying to say, okay, I'm picking one, I'm picking a set, then I'll give it a new name. This time I'm using the set name A prime because to me that evokes the most like this is something from the collection of sets A. Okay, so I'm trying to just say and explain where that A prime is coming from. Second, did we catch how injectivity of F is useful? The proof hinges on X being a single element regardless of the choice of A. Because remember, we need to be able to say this part. X being in the intersection of all of these sets A means that X needs to be something that works regardless of where Y might live inside of each of these individual F of A's, which is where we ended up in our proof, that we're looking at Y inside of F of A, where here A is just some sort of element inside of my arbitrary collection. And I can get some X inside of that set A, but those sets A could be very different. And so the elements of X that I could get could be very different. So it would not be able to just rely on one X being there. And remember, I can't just choose one of the X because that X could live in A prime, but it might not live in A double prime. So it would not live in the intersection. So there's a chance the element X chosen could have been different for each A set that I was going through. And that would spoil this argument where I need X to be in the intersection. Something that I'm going to ask you to do is to give me a function f and a collection of sets A that show that the opposite of this proposition does not hold, namely the one with the containing operation rather than the subset relationship there. So another way to write functions is with regards to the Cartesian coordinates. You may have seen this definition of a function before. One way to write a function is to say that it is a subset of the Cartesian product of x cross y. Defining x cross y here's like, for example, say x is the domain of our function, y is the codomain of our function. Then we could define it as the set of all x and y, where x is a coordinate that is given as an element of the domain, and y is a y coordinate, if you would, that comes from our elements in the codomain. So in this case, you could think of a function f as a subset of x cross y, but it has a special property. And that special property is this. Let's say that you have two elements, x1, y1, and x2, y2. x2, y2. Let's see if these are both elements of the set that I'm calling lowercase f. Let's say that these are both elements of this subset of x cross y. Well, then, if x1 equals x2, well, then remember by what we've been using for functions, if you have that the x value is something, then there's only one real y value that it could go to. So we would say that if x1 is equal to x2, then y1 is equal to y2. That is, you don't have something that happens where you're mapping f of x f of 2 equals 3, and you're also mapping f of 2 to give you 4. So something like this does not happen with a function, because that would not give us a function. That gives us something more general. It gives us something called a relation. So we don't need to be worrying about things like this. So a Cartesian product is one way to write a function in terms of x and y sets. If we get to it, and I'm not sure we're going to get to this point here when it comes to the very final week, we will be using this notion of a function to talk about it in terms of one of the theories that we're going to be talking about. So this sort of visualization of a function as a subset of a Cartesian product is sometimes pretty useful. Think of it as like whenever I draw something like a graph of a function, then oftentimes this is actually how I'm thinking of it. This function is the set of all functions x comma y. Here, x is something real and y is something real. That's how I'm thinking of the function. It's the set of all of these points, and that's exactly what I'm drawing with this function. But notice that I cannot draw the function so that it has two y values associated to the same x value. This would not be a function. The way that we would maybe talk about this is that it fails the vertical line test. It does not have it being the case that every x value is associated to exactly one y value. So now that we've seen this, let's get a little bit of practice here, especially with the Cartesian coordinates, because we see Cartesian coordinates in more contexts than just the definition of a function. Let's take this function g, where it's just going from r squared to r, and that is a function of several variables that takes you g of xy equal to x squared plus y squared. Let's start by finding g of the Cartesian product of -1, 1 and -1, 1. So what does this set look like? This is the set of all points x, y. So this is just saying what this is. The Cartesian product of this is equal to the set of all x, y points such that -1 is less than or equal to x is less than or equal to 1, as well as -1 is less than or equal to y is less than or equal to 1. So that is what we're doing with these Cartesian coordinates, is that the first part of this product is telling us a range of values that the x values could take on. And the second part is telling us a range that the y values of this function can take on. And now we're asked to find g of this set. Well, if we know that x is in between -1 and 1 and y is in between -1 and 1, what is the biggest that this set could go toward? G of this set. We want to claim that it is what we think it is, which is the set 0 to 2. And how would we do this? So how would we say that this is what this set is equal to? First, our intuition tells us that maybe this is a good idea. And that's because the largest values that could plug into x and y are 1. And the biggest, plugging those things in, 1 squared plus 1 squared equals 2. Same thing if I go the other direction. The smallest thing these can be is -1. So -1 squared plus -1 squared gives me 2. This also works even if I try and switch smallest and largest between any of the two coordinates. Finally, the smallest that my values could be is 0, and it's because of the same stuff we were talking about before. F of x equals x squared. The biggest that could be, or the smallest that could be, is 0, because it cannot contain any negative value if it's starting from real numbers. Well, we might need to go through and actually prove this result. My recommendation for this is to say this. Let's go ahead and say that these two things do a double inclusion argument for each of these. Let x be in -1, 1 cross -1, 1. This is for a subset argument here. Then we need to try and say something about where g of x is going to be. So how could we do this? There's a few different ways, and there's some creativity that you can use here as well. One particular way to do this is by looking at the increasing and decreasing nature of these functions. Where are they increasing or decreasing? And to do this, you might look at the derivatives of this function, the partial derivatives, and use that to help out. In fact, that's a good kind of skill to learn. So let's say that you have a point x that's inside of here. That's x comma y is maybe what I should say. That's inside of here. Well, then we have gx of this function is going to be equal to 2x, and gy is equal to 2y. So the only things that I need to check then are the interior points, which is the critical points where both of these derivatives are equal to 0, or I need to be checking on the boundary for this set. So g sub x equals 2x, g sub y equals 2y is one way I could go through and do this. And that seems to be the best and most rigorous way to do this. If you'd like to go through in another direction, something else that you could consider is after maybe instead of checking out interior points and then checking out boundaries like we would in a calculus 3 context, instead what we might try and do is this. Well, if -1 is less than or equal to x is less than or equal to 1, then I would have it being the case that if I multiply through everything by x, well, then there's going to be some cases in which I have, whenever x is negative, for example, we should have that. In fact, I need to be separating those out into those cases, starting with x being in between 0 and 1. Then, well, 0 is going to be less than or equal to x squared is going to be less than or equal to x. Notice what I did is I multiplied everything here by x. And since it's a non-negative number, that keeps all of the inequality directions the same. And that's going to be something that's still less than or equal to 1. Similarly, if -1 is less than or equal to x is less than or equal to 0, then I could go through and multiply everything by -x. And what that's going to give me is something like this. I should get -x is less than or equal to, or rather, I'm multiplying through by -x. So I should be getting, or rather, just by x is fine. So -x is greater than or equal to x squared is greater than or equal to 0. And notice that this is going to be greater than or equal to, or less than or equal to 1 when I go through and write through it. So notice here that I'm getting, when I combine these two things together, that x squared is less than or equal to 0 to 1. What that means is that, well, this is going to imply that x squared plus y squared is going to be in between 0 and 2, because the same sort of rules apply for y squared. So this gives me this sort of inequality for this sort of problem. And that gives me the subset inclusion that I would like, which is that g of -1, 1 cross -1, 1 is now inside of 0 to 2. So my last thing that I could say is that this implies that g of -1, 1 cross -1, 1 is a subset of the set going from 0 to 2. And then I could go the opposite direction. The opposite direction is, if I'm going to go through and do something like this, then I need to say something like, let y, I'm just going to use a value here. Maybe I should be using z, so I'm not getting it confused with the x and y. From the previous part, let z be inside of 0 to 2. Then what I would like to do is try and find a point here that gets mapped to that point. Let's see if something like that is possible. Well, I might try and split this up a little bit. Let's do it like this. If z is inside of the set going from 0 to 1, then g of square root of z 0, something like this, is going to be equal to z, and I can just use the proof to do that. However, if z is inside of the set from 1 to 2, then I could be using g of 1, comma, and then I can go, what is it, something like z minus 1 square rooted, and then that's going to be equal to z as well. And then that's enough for me to show both directions there. The reason I'm going through this, and I won't be doing this each and every time for these examples, is that I want you to see what a full worked out problem looks like. Some of you might wonder these sorts of things when you come into these classes, is wondering how should I be writing out the actual solutions to these problems. Oftentimes what I'll do is I'll just say, here's the general idea, and I'll leave it to you to fill out the details. But this level of rigor, like we have right over here, is typical for these types of problems. So I recommend going through at about this level. You could then maybe go through and see that g inverse going from -2 to 4 and use this part as well. And this one I'm going to leave to you as an exercise, is to show that this is equal to, well, and maybe we can actually get what this one is. We should be able to get to what? It's going to be the set of all x and y such that x squared plus y squared is less than or equal to 4. In fact, we could even say, if we want to be very specific, it's the set of all x squared plus y squared is in between 0 and 4, even though we don't really need this last part. So where's this coming from? Notice here that this is not a set of intervals noticeably for this particular answer here. And that's because you can't actually get that here. There's not intervals that work neatly here. If I'm drawing a picture of all of the points inside of R2 in the domain that map to give me something inside of the set going from -2 to 4, then what I'm drawing is a circle of radius 2. And that's related to the fact that this function g of xy gives you x squared plus y squared. And x squared plus y squared equals r squared. That is the formula for a circle. So pictorially, the way that I'd be drawing this is this sort of set. This might actually be where you start with this problem when you're starting to visualize and get intuition for it. And then you want to be able to show that this set, which is the simplest way we can write this set, is the solution for this part of the problem. We've seen now how f and f inverse commute or fail to commute with unions and intersections. Here I'm using the term commute, kind of like how we would say f times g equals g times f, right? I am saying union and f of x, right? Something like this is equal to f of union of x. This would be somehow a commuting relationship between these two things. Noticing that I'm switching the order. This is a commuting relationship. In a similar way to how I might have a commutative property for addition or multiplication for real numbers. One more operation that we want to check here, and I'm going to leave some parts of this to you, is the complement for sets. What happens if I go through and take f inverse of b complement? Is that the same thing as f inverse of b in an entire set complement? And the answer is yes, that absolutely is true. That works very neatly for inverse functions. However, for images of functions, that does not work very nicely. And that's going to be a homework exercise. I'll leave it to you to take a look through this proof and kind of piece it together based off of the same sorts of principles that we have been doing in our previous parts. At times, we'll come across functions that are both injective and surjective. This is that part that I was telling you about. Injective and surjective together are places in which you can, for each element y and y, find exactly one element, which is f inverse of the set containing y. And that's going to be just one x value, x of y. If that's true for every single y value, then there's actually an inverse function that you can define. That inverse function switches the domain and the codomain. It takes you from y to x instead of from x to y. And it says f inverse of y is equal to that set, that element in the set of f inverse of y, set containing y. So this is now a function because for every 1 point that you map in there, it gives you exactly 1 point back. This mapping is hence well defined, and it is a function. Interesting things to note is that composition works very nicely here. If you have a function f going from x to y and g going from y to z, if these are bijective functions, then so is the composition of the bijective functions. And the inverse of g of f inverse is f inverse composed with g inverse. You might be able to actually prove using parts like this, and I'll leave this one as another exercise, is if, let's say, let's write it like this. Let f x to y be a function. If there exists a function g, this one being from y to x, such that f of g of x in terms of composition is equal to g of f of x is equal to x, then f is bijective. And g is equal to f inverse. So this is a neat exercise that combines a lot of the tools that we've been working with here. So I recommend taking a look at this exercise to see what you're able to come up with. It's taking the idea of inverse functions come from bijective functions. But whenever you have a function that acts like the inverse function for a given function, then actually you know that that function is bijective. So you can go backwards with that. If you have a bijective function, you can get an inverse function. If you have an inverse function, then you know the original function is bijective. What that means is we could have defined bijective functions as those functions with inverse functions. We've talked about how multiple perspectives are sometimes useful here, and that's exactly one place in which we could see multiple perspectives being very useful. Let's go ahead and switch gears here a little bit because I want to talk about series before we get into what we're moving forward through. You'll see this pop up every now and then through homework because this is something that we'll see, especially in the latter half of the class, being very useful. We're going to talk about series a good bit there. So I want to go ahead and introduce series at a level that I hope that we're a little bit more comfortable with. which is that we can recall from calculus that series and functions have a little bit of overlap, which is that there's a notion of a power series. A power series is a function of the form, well, you get a sum from going from some index, and this is a series is infinite, so it's summing infinitely many terms, or taking a look at a limit of a sequence of partial sums for this series. And the terms and what they look like are something like this. You get a sub n, some constant, times x minus c to the n power. Here, x minus c, this is saying that the series is centered at the point c, and this n is saying I'm going to continue making more and more powers for this. Now, you may have seen this in terms of Taylor series. So let me give a kind of a brief example here, which is that Taylor series are if I have a function that is infinitely differentiable, that is, if f is a c infinity function, then I can write f of x in terms of its Taylor series in the following way. I can take it to be centered at a specific point, like f of c, and then I can write this to be plus f prime of c times the value of x minus c. You might notice that actually by itself, this is the definition of the tangent line of the function f at the point c. But I could go farther and get the tangent parabola by going through and taking this little bit of a process here, taking f double prime of c divided by 2 factorial times x minus c squared plus, and I can keep going, taking the nth derivative all the way up here, taking it to the n, dividing it by the n factorial, and then timesing it by x minus c to the n. This is an example of a power series. So you can see you have a constant, at least with respect to x, that you can plug in for each of these terms, times x minus c to the n power. So this Taylor series looks something like this. This is exactly how we're able to show some very neat relationships about e to the x. Because the e to the x has very nice derivatives, when we center this Taylor series of e to the x at c equals 0, what we end up getting is that we get that e to the x is equal to 1 plus, well, every derivative of this is going to give me e to the x, and plugging in c equals 0 for any of this e to the x business is going to give me 1. So this is going to give me 1 times x minus 0, which is just x, plus x squared over 2, plus x cubed over 6, plus dot, 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 plus x to the n over n factorial, plus dot, dot, dot. So this is the Taylor series of e to the x at c equals 0. It tells me how to find e to the x as an infinite series. And why this is useful is if I know kind of the error region that I'd be looking for e to the x, then I don't need to do any exponentiation business to find this function. Instead, I could just be doing multiplication and division and addition and subtraction. Those are the only operations that I need to find a value that's close enough to e to the 1, for example, for this function. If I want to get closer and closer to e to the 1, then I can just keep adding more and more terms. Oftentimes in applications, we're okay to get e to the 1 with some sort of amount of tolerance, meaning that we don't need to get exactly to the value of 2.718 and then infinitely many values after that. Instead, we're more interested in just getting to 2.718, and that's really what we end up needing. So if we're okay with some tolerance here, then we don't need all of these terms. We only need a certain amount. And Taylor's theorem talks about the error function that this Taylor series can result in. And it says you can get close enough to the value in this Taylor series if you add in enough terms. And this is exactly the notion of convergence for a series. And that's this definition down here. So say you're taking collections of not the entire series here, not infinitely many terms, but just starting with maybe the first term and calling that sequence s sub 1. And then a sub 1 plus a sub 2, calling that s sub 2. That's the first two terms added together. Then the first n terms together, that's s sub n. Then we say that an infinite series converges to a limit L if its sequence of partial sums, as defined right here, converges to the value L. So using that definition of sequence convergence that we're used to, and just to kind of remind us here in case it's been a while, we would say that a sequence S sub n converges to L if for all epsilon greater than 0, there exists a value n in the natural numbers such that whenever n is greater than n, and then the absolute value of S sub n minus L is less than epsilon. So this is our trusty little epsilon definition of convergence. It's saying that the sequence gets closer and closer to the limit once you get past any given cutoff point. And you can always get as close as you would like. You can always find a cutoff point for that. So this is what it means for that infinite series to converge, is getting closer and closer to the value of L. There are a few other ways that we can be determining if things converge rather than just using this definition, this epsilon definition for series. We could also be using a sub k and b sub k just being any sequences, parts that make up this series, such that a sub k is less than or equal to b sub k, but both sequences are non-negative. If we get to these two sequences and we know that b sub k converges, well, think of it this way. The thing that you're doing is you're saying, I can sum each of these values of b sub k and get something that is going to be a finite value underneath it. Well, what happens if a sub k is smaller? Well, then the sum of each of those values is going to be even smaller than the sum of the original values that I had. And so that's going to tell me that the smaller part should also converge. Notice that this non-negativity constraint is important because if I allow my values to grow just smaller than b sub k, then the area that's underneath here may not give me exactly what I'm looking for. It may not give me what I need. So notice here that I'm using a little bit of a picture here, and that's exactly what this proof idea is, which is that I'm kind of thinking of these sequences or these series as functions of their own right. Think stepwise functions here. Maybe this is 1, this is 2, this is 3, this is 4, this is 5, so on and so forth. So maybe I'm taking, this is of height 1, this is height 1/4, this is height 1/9, this is height 1/16. And if that's what the heights of each of these are, then to find the area underneath the curve of this function, then what I'm doing is I'm just taking 1 times the y value, and 1 times the y value, and 1 times the y value. And I'm really adding the areas of these rectangles together. So instead of thinking of this as a series, which is just the addition of 1 plus 1/4 plus 1/9 plus 1/16 and so on, I can think of this as the sum of the integrals of these constant functions, which is really, once I write it down, just the integral of a piecewise function. So this is saying that a series can be thought of as the integral of a piecewise function. When I think of it that way, then it becomes a little bit more clear what to do when I have a function that's kind of inside there. Now I'm just using integral properties that I'm familiar with, namely that if I have the area underneath a curve for a function that is in between 0 and this function, well, then the area of that underneath that function is going to be in between 0 and the area of that function. So it should definitely converge. Similarly, if a sub k diverges, let's say, for example, I find out that this thing in red actually diverges, which means that it does not converge, well, then this one's going to give me only an area that is bigger. And so if this does not converge, that means it's actually going to an infinite area. We do not say something converges if it goes to infinity. That would be a diverging sum still. And so because the black lines designate a function that is bigger than the red function, it can only encapsulate a bigger area, so it has to diverge as well. These two parts together are known as the comparison test for series. And our way of kind of understanding how these things look is thinking of these as like step functions or piecewise functions, which are determining whether or not it's finite or diverging by determining whether the area underneath it is infinite. Another way to be determining these things about sequences is through something called the alternating series test. The alternating series test says this. Let's say that you don't have a function that's all positive. Let's say that it alternates. Let's say it goes positive, negative, positive, negative, positive, negative. Well, then there's a few conditions that you can use to determine if it converges at all. One way to do that is this. You can take this sequence and say it's like -1 to the k times 1 over k, and let's take a look at the sum of this one. K goes from 1 to infinity, so that the elements of this are for reasons of niceness, I'll put k plus 1 here, and I'll say 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6. This would be an example of something that would work underneath the alternating series tests. Because if I look at each of these values here, 1, 1/2, 1/3, then the values are constantly getting smaller. They're also converging to 0. It turns out that those two conditions are the only ones I need to determine whether a series converges. And the proof idea behind that is this. What we're going to do is we're going to take a sequence of partial sums, the odd partial sums, and we're going to take a look at those individually. Starting with just the first term, I'm going to take a look at 1, and I'm going to call that my first odd partial sum. Then I'm going to take a look at adding these next two terms together. I'm going to group them together in a special way. I'm going to write this as S3 minus 1/2 minus 1/3. Notice that because of our condition that each of these numbers is only getting smaller, 1, 1/2, 1/3, so on and so forth, this has to be a positive number. So I'm subtracting a positive number, meaning that as I go from S1 to S3 to S5 to S7, that this is a decreasing sequence. You might be familiar with the monotone convergence theorem, which says that if I have a decreasing sequence and it's bounded, and we could see that this one is bounded after we take a look at the even partial sums, then we can actually get a converging point for this sequence. So that's the idea behind this. We'll maybe talk about this a little bit more once we get to the monotone convergence theorem. But this test says all I need to take a look through these things is to try and piece things together in terms of pairs or odd partial sums or even partial sums. So any sequence that decreases and goes to 0 is good enough when composing an alternating series. Now, something else that we'll see a lot of is not just infinite sums. We'll see finite sums as well. We talked about how the sum of the first n numbers is n times n plus 1 over 2. But the limit of finite sums gives you this infinite sum. So finite sums are sometimes useful to study. If we can say something about finite sums that make up an infinite sum, we can often say a lot about the limit of those finite sums. So that's something that uses these limit theorems that we've been using for sequences. So we're kind of using this dual nature of series as an infinite sum, as well as the limit of a sequence. A special type of finite sum is this one. You can see that this is the sum from k goes from 1 to n of 1 over k times k plus 1. If I rewrite that a little bit using maybe partial fractions or something like this, or some other sort of fraction decomposition, then I can write that as 1 over k minus 1 over k plus 1. Writing out what this infinite sum looks like is of note, because I get something like 1 over 1 minus 1 over 2. This is the case when k is equal to 1, plus if a k is equal to 2, plugging it into this formula, I'm going to get that this is 1 over 2 minus 1 over 3, plus you see that there's a little bit of a pattern going on here. 1 over n minus 1 over n plus 1 would be the final step when k is equal to n. And notice too with that pattern that a lot of the terms end up canceling. See here that I have some inside terms, kind of the negative 1/2 from the first k equals 1 and the positive 1/2 from the second pairing, k equals 2. Those are going to cancel through this. If I continued this and looked at the k equals 3, then the minus 1/3 is going to cancel with a minus 1/3. Similarly, this 1 over n is going to cancel with a minus 1 over n in the k equals n minus 1 pairing right before it. What I end up being left with here is just 1 minus 1 over n plus 1. This is known as a telescoping sum. Telescoping because I like to think of it as like you take a telescope and you can stretch it out all the way, but then you can collapse it. And it's really just all the way down into one thing. That's kind of how I think of it. It's like you get one of those stretch out telescopes and you look through it and then you put it back together and all of those terms just collapse together to give you a small little compact expression. So that is a telescoping sum where the inner terms end up canceling out. And if I went through and did this infinitely, you could see that the limit of this telescoping sum, and this one in particular that we've been looking at, is 1. And then that's something like that is very nice and straightforward to see. Namely, the difference between the finite sums and the infinite sums grows very, very small as time goes on. The difference between 1 and the finite sum 1 minus 1 over n plus 1 is 1 over n plus 1. And if I let n go to infinity, 1 over n plus 1 is going to go towards 0. There are also geometric sums, and so this formula is going to be useful for us. This one of taking something like 1 plus r squared plus r cubed plus all the way up to r to the n. So this can be written in a very special way, and it comes from the fact that if I multiply this value, this 1 plus r squared is all the way up to r to the n, if I multiply this times 1 minus r, then what I'm going to get is a telescoping sum in the following way. I can take 1 minus r, multiply it times 1, and that's going to give me 1 minus r. Plus, I can then go through and multiply it times r. So this distributing this 1 minus r is going to give me r minus r squared. And then I can multiply 1 minus r times r squared. That's going to give me r squared minus r cubed. And you can see that these end up telescoping as well. The r's cancel, the r squareds cancel. And what I end up with is something like this, where the r to the n cancels again. And I'm left with just 1 minus r to the n plus 1. The last step is to find what this is equal to. I just need to divide both sides by 1 minus r. When the absolute value of r is less than 1, then this actually converges. It doesn't have to converge if absolute value of r is equal to or greater than 1. You can kind of check these things out if you would like. I recommend it, in fact, to see that if I take 1 plus 2 plus 4 plus 8, etc., a geometric sum, to be sure, that one's definitely not going to converge to, well, anything that this thing tries to tell us it might converge to. I think it would say -1 if I tried to plug it in there. So the infinite series, 2/3 to the n, like this, is equal to 1, is going to be one of our lemmas for something that we're going to see in the next section. So let's see if we can show why this lemma is true. So I see that this is almost a geometric series. Notice that geometrics are r squared, r cubed. But notice the only thing that's being raised to a power of n here is the 3, not the 2. So I actually have to factor that 2 out. And what I'm left with is going to be 2 times the sum as I goes from 1 to n, infinity of 1/3 now to the n. Now I can go through and use this formula that this is the limit of, or 2 times the limit of, limit as n goes to infinity, of 1 minus 1/3 to the n plus 1 divided by 1 minus 1/3. At this point, I can now go through and calculate, see what I end up getting here. Should get something like this. Well, notice here, first of all, that this sum is going to involve 1. So I actually need to go ahead and incorporate one last thing here, which is that I need to be subtracting by 1. This is something that I see a good bit when I go through these sorts of problems, is that I have to be careful with these indices. This index doesn't start at 1 like this geometric sum did. This one starts at 2/3. So I need to be subtracting by 1 so that these two things match up as closely as they can. So I'll need to subtract this by 1. Now I can go through and take this limit. I should get that this is 2 times I can go ahead and take that limit actually. This one's going to go to 0. So I'm going to be left with 1 minus 1 over 2/3 minus 1. That's going to be 3/2 minus 1. That's going to be 3 minus 2. And that's going to give me 1, like I would like. So this lemma kind of shows us how geometric series can be used in these contexts. So what have we talked about? We talked a lot about different types of functions and the utility with it, power functions, series, how to show that these things converge. What we're doing here essentially with power functions, we'll talk about more later on about how power series converge. It'll be a good Calc 2 refresher when we get to that point. That'll be around in week 6. But until then, we've got a lot to chew on. We see now how sets and functions interact and how that can add a little bit of a complication to the whole story. The fact that functions and sets can now interact means that we need to be thoughtful about how they interact, right? Finding answers to problems like this means that we need to think about these in terms of the double inclusion, but we need to be using the definitions of functions to get us there, to help us out. Notice that our proofs with these sorts of functions as well kind of deal with a lot of these new definitions. At the end of the day, functions here are adding another layer of definitions for us to be careful about. We also have learned that inverse images actually work nicer than images of functions do. And that's going to be a relevant detail for us as we go in through this class. So my recommendation is, now that we've gone through these first 2 sections, I would go ahead and take a look through the homework. And I would start trying to find some of the questions that look like things that you could tackle based off of these 2 sets of problems here, these sets of notes, and start trying to work through them. If you think there's something that maybe I need to be looking at a little bit more closely, try looking through the notes for something, right? Try looking through the book for something that is useful there. So try now taking a look at these homework problems and start getting a leg up on these sorts of problems. Our next section is going to go in a different direction. You may have already seen it. It's talking about cardinality and the different notions of infinity. It's not going to be related to this sort of stuff. So that's it for today, y'all. Thank you so much. Have a wonderful day.